So this is a brief introduction to OpenFabrics interfaces, libfabric. For those, you may hear the term OFI. This is part of OpenFabrics. My name is Sean Hefty. I had created my slides before they sent me the template with the girl looking at the code, so I don't have the girl looking at the code. Sorry, a woman. Yes, I just have a blue background here. So I'm one of the maintainers of OpenFabrics software. I think three of the user space app libraries, a daemon and user space, some of the Linux RDMA kernel stack as well. I've been working with OpenFabrics for as long as it's been in existence, and with Intel for a little over 20 years, primarily focused on InfiniBand and HPC software. So what is libfabric and what is OFI and what are we trying to do with it? So we kind of go back just a little bit to where we started at. This really goes back about 3 years for the motivation as to where we are with OpenFabrics interfaces and libfabric. At the time, libIBverbs was really the main software component when people thought of OpenFabrics and InfiniBand and HPC applications. This was the interface that a lot of applications ended up coding to. So it was widely adopted as the RDMA API in the industry. It is shipping with upstream Linux, so it's available in the distros. And there's some additional libraries that are part of work with libIBverbs that also ship within the distros. Actually, the Linux RDMA stack is in the kernel and upstream. And this is really intended as kind of a unified API for RDMA type devices. However, when we start looking at the API itself, and the implementation, you see that it's designed around the InfiniBand architecture. It's very clear when you're looking at the software interfaces that it's talking about InfiniBand. It was designed for InfiniBand specifically at the time it was developed. So it's targeting a very specific implementation of hardware. Verbs as an interface by itself is really a description in the InfiniBand specification is talking about a hardware abstraction, not a network abstraction. So for many applications, it's too low level. I mean, even in OpenFabrics, we've heard this endlessly over the years, where application developers were complaining that this is not the interface they want. It's too low level. It's too difficult and too many lines of code to actually work with in order to have the application do anything. So it takes a very long time for the application developers to write to this. We also see that we have additional hardware and fabric features occurring. And one of the results of this is that as these new hardware features occur, because this verbs interface is so low level, that we're having to continually change the verbs interface to adapt to these new hardware features. And as a result, we end up with the multiple APIs being developed. For example, Intel TrueScale, they use PSM as their interface, so they have an alternative interface than verbs. Cray and IBM both use different interfaces than just verbs. So even though you may support verbs, they have other interfaces that are supported natively that work better for their hardware. Even Mellanox has MXM as a proprietary interface that gives them better performance and scalability because it can take advantage of the hardware. So the solution went to OpenFabrics, went to their technical advisory committee and said, hey, we have these new types of devices coming out. We have devices here. We're running into issues that we can't expose these capabilities through verbs. Applications are not happy with verbs. At the time we presented this, there was no way to even add new capabilities to the libIBverbs. So that's since been corrected, and there is now a way to try to extend libIBverbs and have additional features extended. So we believe that libIBverbs will continue to exist as part of OpenFabric software. But there's additional types of hardware that's going to be available through OpenFabrics that's available today, even like the TrueScale, OmniPath, Cray has hardware that doesn't work very well with verbs. So we wanted to try to leverage the open source community. So okay, we already have OpenFabrics, we have these developers engaged. What can we do to try to help expand OpenFabrics? So if you go back a little bit before this, right? So OpenFabrics was originally named OpenIB. The entire point of OpenIB was to we had multiple InfiniBand vendors, each creating their own software stacks. OpenIB at the time formed, said, well, let's have one software interface, libIBverbs, that works with all these InfiniBand devices. Later, OpenIB adopted iWarp. They said, okay, well, we have iWarp devices now. Let's allow iWarp in. They renamed from OpenIB to OpenFabrics. and now they had support for iWarp devices. One of the issues was because the interface was still libIB verbs, iWarp devices had to pretend to be InfiniBand devices where it made sense. So even if it didn't make sense, they still had to try to be an InfiniBand type device. So we want to try to leverage the same community and say, okay, OpenFabrics needs to expand even beyond verbs. So we have InfiniBand, we have iWarp, we want to be able to expand to other types of hardware. And we don't know exactly where the hardware is going to end up at, but we know that there's going to be additional capabilities in hardware from different vendors, and we want to be able to try to make those available. For our interfaces to work, we wanted to try to switch from this bottom-up approach of saying we want to expose the hardware interface up to the application to we want to have it be application-centric. So we want the applications to define what are the features they're looking for and let them drive the interface. So as part of the working groups, the OpenFabrics interface working group formed, OFIWIG. We invited the application developers in and said, okay, be part of this group, give us your requirements, what do you want of these interfaces? What is the application really trying to do? And let's let that define the interfaces. And then we'll make sure we have an efficient mapping down to the hardware for that. We wanted our interfaces for this to be scalable. So we're not just looking for really easy to use. We want to make sure that what we have is easy for developers to use, but also focus on the scalability of it. We want to make sure that we're not having data structures that span multiple cache lines. We want to minimize the size of memory being used for addressing. So if I'm talking to 1 million nodes, I want to make sure I'm not consuming 64 gigabytes of space just to do addressing to those 1 million nodes. We want to minimize the instruction count. Again, if you're looking at 1 million nodes, each doing 1 million messages per second, an extra 10 instructions for every message adds up really quick. So we want to try to remove any instructions that we can out of those critical paths. The other goal we had, again, we're going through the open source community. We're trying to create this for any types of hardware. We wanted to make no assumptions about how the hardware may be implemented. So the interfaces are designed to be implementation agnostic. We wanted to have a good impedance match from the application down to the hardware, so we had to really analyze what are the applications trying to do, what can the hardware do well, and do we have the best fit there that we can for various types of hardware. So as we develop libfabric, we're actually looking very closely at, does this map well to InfiniBand? Could an InfiniBand device fit under here very well? Does it map well with iWarp? Does it work well with a raw Ethernet device? Devices like Cisco has a device that does UDP offload. Can it support that sort of device? Does it work with OmniPath, Cray, IBM? So we're looking at all these different devices and how well do those fit under libfabric and usable in an optimized implementation. So this is the actual charter of the working group. So I'm one of the co-chairs of the OFIWIG. If anybody's interested, that's on the slides. We have a mailing list you can join. You can sign up if you want to attend meetings. So even though this is part of OpenFabrics, there's no requirement to be a member of OpenFabrics to attend these meetings or to participate. All the development is done in GitHub in the open source. And one of the goals here is the belief is that if we move from this bottom-up approach to an application-centric driven interface, we can allow fabric innovation to occur quicker. So if you have what the application needs, you can add new hardware features. The applications can immediately take advantage of those hardware features without having to recode, just by modifying the providers underneath the application. General model that we're using for development. Obviously, we started with a very rough model, but most of our work starts with this requirement analysis. So when you go out to the community and you say, what do you want to have an application, and trying to understand their requirements, what you often get are solutions. So you say, okay, what does the application need here? And they give you a solution, and that solution is often tied based on their current implementation. So it really takes a lot of work, and we probably spent the first 6 months of the OFIWIG spent just trying to break down those requirements, saying, well, what is the application really trying to do? That way we can abstract that requirement out and come up with an API that really suits what the application needs and also works well with the various hardware that we're trying to implement under or over. I mentioned as we went through this development process, we do look at a very wide variety of devices. So this is open source. It's not just an Intel-looking API. We're trying to make sure this works with any application's API, or sorry, any vendor hardware API or interface. We currently have a quarterly development cycle. So as we're developing the library, basically every 3 months or so, we're trying to get new releases out. We're doing a time-driven approach, because what we've seen with OpenFabrics, especially with the OFED releases, is sometimes the OFED releases can take a very long time to come out. And because it can be so long between major releases, it tends to, people want to push as many new features in as they can because it's such a long time before the next release. So we wanted to try to break, at least from libfabric, break out of that model and say, well, if you know you only have to wait 3 months, it's not too bad. If you miss this release, wait 3 months, we'll get you into the next release. So we try to use a time-based release. So I mentioned the application requirements. So when you go out and you bring in the applications developers, you say, what do you want out of these interfaces? Went to the MPI group, went to SHMM. What do they tell you? They come back and say, give us a high-level interface. And then in the same presentation, the exact same presentation, they say, give us a low-level interface from the same group of people. All right, so what this did is this actually drove the direction of what we were doing with libfabric. Some people wanted high-level, some people want low-level. Right? Some people, I just want it very easy to use, make it very easy to code to. Right, which sounds really nice. You'd like to be able to just write your application very quickly and get it running over libfabric without having to spend a huge amount of time trying to understand what every little intricate piece is. I don't need to modify queue pairs and walk through queue pair states. At the same time, there are some end users that really need to get the highest performance out of their hardware. So their idea of looking at an abstraction, saying, well, this is a nice abstraction, but my hardware doesn't do exactly what you're saying. How can I get to that piece? And that kind of builds into the architecture we've designed for libfabric. So from the design perspective, again, we're implementation agnostic, and we kind of expand a range of usage models. So here I just broke it into two. I had a very easy model, so you have the easy button, and then you have the advanced model. But in reality, you're really in a range here of how advanced do you want the application to be. You can go over and tweak it down to a very low level, or you can come back and start easy. Or maybe start easy and then find where you need to focus your development effort to try to optimize for the particular hardware you're looking at. So in the easy mode, again, from the API's perspective, there's not like an easy button. This is conceptual here, but from the easy mode, basic usage, we want to move functionality underneath libfabric. So if a bunch of applications have to do the same amount of work, we want to push that down under libfabric so it only needs to be done once. We can have a single implementation, debug it, optimize that code once, and all applications can use it. At the other extreme is the application really wants to know, well, what does my hardware that I have in my current system do, and what does it do well? And we want to be able to expose that capability up to the application and say, well, it does exactly these 3 things well and this one thing over here fairly poorly. So if the one thing it does poorly, do you need it or not? And do you want libfabric to handle that for you, or do you want to deal with trying to work around that solution? So this is the general architecture. The current focus with libfabric and our current development is really trying to enable applications. So from the libfabric perspective, I kind of showed here at the breakdown, we've got these 4 services. Sometimes you'll hear people say these are interfaces, sets of interfaces. So I kind of broke into these different services. Now for most applications, the obvious ones are these data transfer services. So we have one-sided and two-sided communications. So message queues to send and receive messages, similar to a FIFO. We have tag matching APIs, which work very well for MPI applications. We have one-sided RMA operations. We have full sets of atomics that map very well to MPI and to SHMM. In addition to the data transfer services, obviously we have some sort of completion services. The APIs, one of the requirements we got was they wanted all the APIs to be asynchronous. So we have asynchronous support in all the APIs. So we need to be able to provide some sort of completion notification. And again, the completion services, I won't go into too much detail on these today, but the completion services are designed around making sure we have minimal cache footprint. Right? If an application only needs to look at 8 bytes of completion, we only give them those 8 bytes. We don't give them 64 bytes and have them ignore 56 bytes and look at only the 8 bytes they care about. So we have these interfaces optimized around, for example, successful completions and only giving back the application the data that they need. We have lightweight completion services. So in this API, we have completion counters. So some of the applications we looked at, what they were doing when they were getting completion data was simply incrementing a counter. So, well, if we can push that under, then we don't even have to report the completion. Just let the counter get incremented underneath. For communication services, obviously for an HPC, you're typically using unconnected communication. But libfabric, some of the applications we looked at were socket-based, were database management systems, Oracle, IBM DB2, and they needed connection-oriented services. So we do have connection-oriented services as part of libfabric. The address vector component, this is our sets of interfaces designed around abstracting the fabric and abstracting the addressing that may be particular to that fabric. So whether you're using an Ethernet-based fabric, an InfiniBand-based fabric, OmniPath-based fabric, for an application they can be oblivious to whatever that addressing scheme is and how those addresses get resolved into something useful by the hardware. The address vectors are also designed to be highly scalable. So when we're designing these interfaces, for example, we designed into the interface the ability to share this addressing information between processes. So we don't have to have every process have the same address. We can now start sharing it. And by pushing it into provider, we can optimize how address resolution occurs, for example. If I have to convert an IP address down to an InfiniBand address, that resolution doesn't need to be one address at a time. I could do it in some sort of group optimized method. And then the control services is really where the application starts with the interface to identify what are the hardware features that they're dealing with, what hardware is available, what are the capabilities of the hardware. And I call here services. This is really a single interface. Right? It's a single function call that an application gets into that has this one data structure. But through this service, they identify what capabilities are available, and the application also makes a request as to what are they looking for and what sort of communication are they dealing with. So if the application is doing RMA capabilities, they pass that through the discovery services. They say, I need RMA capability. Give me the best use of RMA. And now that pushes it down to the provider to say, here's my best implementation of RMA for you. So libfabric defines these interfaces. It defines the behavior of these interfaces. In almost every case, so especially in the speed path, so completion operations, the data transfer services, libfabric doesn't actually exist. It just defines the interface. The application is talking directly to the provider. So there's not a middle layer there. The application has access directly into the provider code. We even have a direct mode in libfabric that lets an application write to libfabric, compile with like a direct operation, and then it basically compiles the provider code directly into the application. So if an application wants to use a different provider, they need to recompile, but at least they wouldn't need to recode. But that does allow the compiler to at least use like an IPO type feature and say the application, he can look at the application, he can look at the provider and throw out branches or any checks that aren't necessary that would be if you had a dynamically linked library. So at the top layer, we have functional libfabric that does good performance on several different hardware vendors. You can see there's a lot of applications that have been enabled to run over libfabric. Several MPIs, SHMEMs, GasNet, some socket-based type applications. So we're trying to make sure that these applications can use libfabric. And again, there's different usage models of libfabric. So libfabric is not like a one size necessarily fits all, that I have to write this way to libfabric. For example, OpenMPI has two different implementations of how it talks to libfabric, depending on what features are available. On the bottom side, you can see the different providers that are available today. So the dark blue, all of those are available except for the UDP provider. So one of the other objectives we had, we wanted to be able to make it easy for developers to write to libfabric. So we have a sockets provider that runs over TCP that lets you, for example, just run libfabric on your laptop. Or it can also run on Mac. So we do have libfabric available on Mac, which developers apparently really like, to be able to just run some of this stuff and do the development on Mac or just a normal Linux box. We have a verbs-based provider that works over in current verbs hardware, so anything running InfiniBand or Rocky or iWarp today. And that's the capabilities there are being expanded. Cisco has a native provider, so they write directly into their provider down to their hardware for their user space-based Ethernet NIC. Obviously, we have support for Intel's TrueScale and OmniPath in part of libfabric. Cray released a native provider that's coming out. So it's in the current code upstream. It's in the 1.2 release, which is coming out at the end of this year. It's in the current RC. So Cray has support for their GNI hardware. And then we also have some support for Mellanox hardware that's provided that's layered over MXN. That gives us additional scalability features that we wouldn't get through writing to Mellanox hardware through the verbs interface, for example. And there's also two other, I'm listing these experimental. So we have a native provider that runs over IBM Blue Gene hardware that we've used to scale out to basically 1 million ranks. So we make sure that we can scale libfabric out and it can work over very large scale systems today. I don't know that that will ever be made available, but we have it internally so we can at least test out that the interfaces do exist and do run. And then there was a grad student who actually took this and ported libfabric on top of A3 Cube, an interface cluster that they support. Again, I'm listing that one as experimental because I don't know what the support status would be because it came from, I think it was a master's student who did that work. So looking a little bit more about what does libfabric look like from an application user viewpoint. So again, going back to kind of the two modes, easy versus extreme. In a very simple case, an application says, hey, I want reliable unconnected communication. So in OFI terms, we call that RDM, reliable datagram. It matches the same syntax that sockets uses. And they want tag message capabilities. So if a provider can give you just these two things, it can work with most MPIs, for example, like Intel MPI, MPitch, OpenMPI. If that's all you gave them, they could make it actually run over the hardware. So if we had, like, for example, Cisco, their US NIC does essentially unreliable datagram communication, right? It just sends receive datagrams. Again, at a similar level, Intel TrueScale does something very similar. Conceptually, it does basically an unreliable datagram type transfer. It has additional features, but from one level, that's really what it's doing. So if you need reliable communication built on top of that, what we're really trying to do with libfabric is push that capability underneath the interface. We don't want every application having to re-implement reliability. So if we can push that under, we can have a single version of the reliability, we can optimize that version, and then the applications don't have to end up dealing with it. And this is kind of the very simple mode. But it does require trust from the application that the implementation inside libfabric will be correct. And hopefully, since we're dealing with open source, if there's an issue, right, you can go in and actually try to fix it. So you can pull the code, you have access to modify it. In a more advanced usage, we get into looking at what are the capabilities. So say I want reliable communication, I want it unconnected, I want tag matching, but what does the hardware really give me? What features am I missing out on? So libfabric exposes through its discovery interface and capabilities, attributes, and Modebits, which I'll talk about those here. So the capabilities, what type of communication are we dealing with? This goes back to the data transfer services I mentioned earlier, RMA, message queue, tag matching, atomics. Which of those are you wanting? We also include certain permissions, right? Some applications say, well, I want RMA capabilities. Are you wanting to be able to initiate those? Are you wanting to be the target? So we want to give at least a possibility that we have some security protection where an application can say, I only want to initiate RMA. I don't want to accept any incoming RMA against my memory. Then there's certain features that applications wanted. And in a lot of these cases, these features, these are what applications are desiring, but current hardware may not be able to do it. For example, RMA events. A lot of applications wanted to send an RMA operation to the remote side, and the remote side needs to be notified that the write has occurred. Well, a lot of hardware today, once you send that RMA request across, say it's a read or a write, you actually have to send another message that says, I just did a read or write to your memory. Right, so we want to be able to add a feature that says, well, if I'm going to do an RDMA read to the remote side, does he have the ability to at least know that that occurred without me sending a separate message? So we want to build those sort of features into the API. So, well, you can do the RDMA reader, right? The remote side will be notified of it without you having to send a separate message. So you can now start taking advantage of it from an application viewpoint. One other one to mention is multi-receive. Right? Current InfiniBand and IWARP hardware, if you try to send and receive messages, you have to post a whole bunch of individual buffers. Right? You fill up this receive queue. You say, here's an 8K buffer, 8K buffer, 8K buffer. So you post like 1,000 8K buffers. And you're going to consume that entire 8K buffer even if you only receive, say, 100 bytes. Well, applications were asking for said, I just want to give you one big blob of memory. And there's hardware that does this, right? The Cray hardware can do this. Say, here's 64 kilobytes of memory. As data comes in and you receive a message, just start filling up that buffer and tell me when I have received data. Don't make me give you these separate individual chunks that's based on the maximum size message. So that's a feature, again, that becomes hardware specific that an application can take advantage of. Some of the attributes that we have defined. So a lot of the attributes are looking at these limits and behavior of the interfaces. So a lot of people, when they look at that stuff like limits, they're thinking the size of a command queue. How many entries do I have in a C queue? So libfabric defines these concepts a little more abstract. They're really looking at how many are supportable by the hardware. So just because, for example, a vendor says I can support 20 million endpoints. Can their hardware really support 20 million endpoints, or they just can have 20 million addressable units? The hardware may only be able to support, say, 8K worth of actual active endpoints. And we want to be able to expose that up through these interfaces. So when you have a resource manager, the resource manager can say, okay, I have access to 20 million endpoints. The hardware can only actively deal with 256. How do I want to assign those 256 active endpoints among the application that's trying to run? Right, so that's the behavior we're trying to give, or the features we're trying to give to the application. So some of the attributes, stuff like progress, and this is driven, progress is really driven almost from a bottom up in this case. So these are asynchronous interfaces. So if you submit an operation, say to send a message, does the application need to do anything after that to ensure that that message is reliably sent? Right? So in that previous slide, I had this datagram hardware, and I'm trying to put reliability on top. Well, where does the retransmission come from? Am I forcing the provider to use a thread to do this? Or am I letting the application know that says, hey, if you want me to be able to use reliability, you need to call back into me at some point in time? Right? So that's one of the things you want to expose through these attributes is a progress mode that says the application, if you call me back, if you're always going to be calling me, I don't need to allocate a thread. I'll just use the application thread to ensure that I'm making forward progress. The threading, a lot of this came from the threading definition we have, came from the Shemem work. So the threading was looking at if I'm accessing hardware and I have multiple threads, how can I ensure that I don't have locking? So what we wanted to expose through the API was a way to identify which resources would end up, if the application accessed these two resources by multiple threads, would require locking. Versus if they access these resources in separate threads, no locking would be incurred. So we wanted to expose not just whether we're thread safe or not, but how the application can make use of multiple threads accessing multiple resources without incurring any synchronization penalties. And then the Modebits. So even if we went through all this, we're trying to drive from the top down, there are still cases where the provider simply cannot support what the application is really wanting. So there's cases where we want to be able to expose from the bottom up that says, you know, as an application, if you did this for me, I could give you better performance. For example, the second bullet there, the context field. If you submit a request down to the application, this provider underneath is going to have to track this request. Sometimes the provider tracks it automatically. Sometimes the provider needs to allocate some data structure. If the application, like MPI, for example, is already allocating a data structure to track the request, if they allocate just a few more bytes of memory and pass that down for the provider to use, right, you avoid having to allocate another structure off of a pool. So these are usages that the provider is really sending up to the application saying, hey, if you do this for me, I can give you better performance. Buffer prefix, right? This is a case that comes with InfiniBand. With InfiniBand, if you're using datagram communication, the receive side ends up with an extra 40 bytes of data that's carried over from the GRH, a global route header, right? So some network header pops in the user buffer. We need to be able to provide a way that says, if you ignore the first 40 bytes, for example, of any received message you get, your data is 40 bytes into it, and everything will be faster. Otherwise, the provider is going to have to allocate that 40 bytes and put it before the application's buffer. So Modebits are really things applications don't want to do, but are better off doing for performance reasons. So for the data transfers, obviously we're starting with basically just an endpoint. Again, very simple case. An endpoint conceptually just points to two command queues, a transmit queue and receive queue. As data operation completes, goes into some sort of completion queue, maybe a counter. Like, very easy for an application to try to deal with this. But as I mentioned, we want to be able to work with resource managers trying to make sure they're not oversubscribing the hardware. So we want to be able to expose saying we only have 256 command queues available. So now a resource manager can start looking and say, okay, I have 256 command queues. I'm going to talk with 1,000 remote peers. Which of my endpoints do I want to share the command queues with? So we have both shared transmit and shared receive, or we call them context, command queues essentially, that an application can now start assigning. The alternative to that is to have what we call scalable endpoints, which says, well, if I have 256 command queues and I'm only going to allocate, say, 32 endpoints, am I going to waste my hardware? Or can I have an endpoint that has multiple transmit queues? Right? If I have the hardware available, let me use all the transmit command queues that I have. So we provide a way that says, okay, these are your command queues. If you use a scalable endpoint, and this depends on the provider supporting it, but scalable endpoints allows you to have multiple transmit queues for the same addressable endpoint. So rather than having, for example, 4 different endpoints, which would increase your addressing by 4, right? You have one endpoint, so you have one address, but you still get to take advantage of multiple transmit queues on the outbound side. Similar on the receive side. And each transmit queue can be used to allocate per thread, so each thread can have their own transmit queue without having locking. If you had ordering, you can break the ordering up so you don't have large RMA operations, for example, behind the message, or a message behind a large RMA operation. And to give you an idea of what we're looking at the API level, just a comparison looking at verbs. So what libfabric looks like compared to a verbs interface. I'm not trying to pick on verbs here. This is just the one that was widely used by OpenFabrics. But these issues apply to a lot of APIs, right? If you look at Network Direct or DAPL or AIO, right? They have the same sort of types of issues. And what we're looking at when we're analyzing the API is how many bytes does the application have to write in order to submit a request. So let's say I want to send a buffer. I want to send a single message, just one buffer, one message, send it out. If I'm dealing with libIB verbs, I'm looking at writing about 84 bytes of data. Right, unless I'm doing a micro benchmark where I can cheat and pre-format this request. You're looking at 84 bytes of data having to be written just to submit the operation. On the libfabric side, the same sort of operation would be basically 40 bytes worth of data. Right, and that's going to be 40 bytes that's written onto the stack that makes the function call. The other thing we can look at in the API is whether or not the API will introduce branches in the implementation. So if we look at, like, the send work request in verbs has this next pointer. I can chain these work requests together. Right, not a lot of applications ever do this chaining, but you can chain the requests together. Well, because you have this field that says I could have chained, the provider now has to incur a loop. Right? So a loop ends up going to be usually a write at the beginning of the loop, an if condition at the beginning of the loop, and then a write at the end of the loop. So you have at least a branch here. You may have 2 additional writes occurring because you have this one field, even though the field might almost always be set to null. The number of next gather entries. So if I'm using multiple scatter gather entries, I'm going to have a loop. But if I say I just want to send a single message buffer, Right, I'm still taking a penalty here. I still have, again, another loop. So I have 2 more writes and another loop. So just those 2 fields is going to cost us at least 2 branches and probably 4 additional writes. The opcode, so the verbs carries with it the opcode indicating whether I'm doing a send, I'm doing an RDMA operation, read, write. Right, that opcode needs to be decoded. Most of the implementations, that decode is done using a switch statement. So again, you have another branch. Maybe you could take the opcode and make it a jump into another function pointer table, but usually the implementation ends up doing branches. And then we have flags to indicate what the behavior. So it changes the behavior. Do I want a completion or not, for example? Again, the flag field ends up doing branches. So in the best case, you're looking at probably 5 branches with this code. So there's another branch. I'm not showing the full API here. If you look at the implementations underneath, usually you're closer to about 20 different branches occurring when you include the loops. All right, with libfabric, we're trying to move stuff like the opcode. That's going to be implied by the function that's being invoked. The flags, ideally the operation flags will be set up front, so you know what the operational flags will be for any RMA operation or any send operation before the application actually gives it. And one of the things this allows us to do, by moving more of this into the initialization code, we can actually pre-format, for example, commands to the hardware. So you can take, you know what the command is going to be, most of it. You can actually have that buffer sitting there ready to go. You're not having to format the command to the hardware on each request, which allows you to further reduce the number of memory writes that you're having to incur. And the memory footprint. Again, I'm using verbs as the example here. If I'm using unconnected communication with the verbs interfaces, we're looking at about 36 bytes of data minimum per remote peer you're trying to communicate with. All right, libfabric defines, again, a simple case is 8 bytes worth of data. And in the design of libfabric, when we're looking at these address vectors and how we want to deal with addressing, one of the things we're looking at is, we want an easy mode, we want to be able to minimize memory. So we actually ended up with 2 different ways of dealing with addressing. So we have what we call a map address vector and index address vector. In the index case, the application, if they're accessing a remote peer, they just do it by a simple index, 1, 2, 3. Right? So for some applications, it works very well. They take an index from the application coming in, they pass the index straight down. And what that allows is you can have now a very small footprint to address millions of remote peers. The cost of that is the index you're given may require a lookup in the provider, right? A lookup into an array or some sort of calculation. But in terms of memory footprint, we can take what would be maybe 36 bytes per remote peer, and we can shrink it down to you may only require a couple hundred bytes total to access millions of peers. It depends on how the fabric may be laid out. Right? If I know the peers are in specific addresses, lids 1, 2, 3, 4. It makes it very easy for me to calculate, given the index, where is that remote peer going to be. So the release schedule, the first release was end of Q1 of this year. It had, again, we're trying to quickly do the development of libfabric. We're trying to enable the applications. So we need to get the applications enabled before the providers say, yes, we're going to support it, right? You're in this kind of, which one comes first? We need to have all the providers ready or the applications ready. So we're trying to get the applications ready. There was a new release at the end of Q2, a bug fix release, and now we're at RC1 of the 1.2 release, which adds additional providers. So it adds the MXN provider, the Cray provider, the OmniPath provider is now in this next release, and then enhanced verbs. So the enhanced verbs is the support to have MPI run over the verbs provider. So the current verbs provider in the 1.0 and 1.1 release only supports connection-oriented communication. So the 1.2 release will have basically the reliable datagram support in the verbs provider. And then sometime probably towards the end of 2016, we'll look at doing a release that has extensions. So we built up a set of extensions, or there were certain features that we didn't feel comfortable putting into the 1.0 release that we want to re-examine. And stuff like, for example, multicast was not added to the 1.0 release. We want to get that in probably in the release sometime at the end of next year. And the plug for other information. So there's a tutorial where we'll go into a lot more detail on what libfabric is and how you use it and how you would code to it. all these attributes and modes I talked about. So that'll be on Monday. There's a BOF on Tuesday. That also, so the OFIWIG has a subgroup that's focused on data storage and data access. That's primarily focused looking at the NVM use case. So there'll be a BOF there where we talk about, what do we need to do to support NVM, for example, and my disclaimer. Any questions? I think there's like 5 minutes.